Okay, welcome back. So now we're going to talk about sequential decisions. So an intelligent agent doesn't carry out a multi-step plan, ignoring information it receives between actions. So you don't sort of make up your mind what you're going to do and then ignore all the information you find. Instead, you're going to use the information you find on the way to make your decision. Okay? So more typical scenarios where the agent observes the world, acts, observes the world, and then acts, and so on. So you keep having this sequential decision about observing and acting through the world. So you don't ignore, when you're acting here, you're going to take into account your whole history of actions and observations. What happens is subsequent actions depend on what's observed. What I do here depends on what I've observed. What I observe at this point depends on what I did here, right? So they're all interacting. So this action should depend on this observation, and this observation depends on the previous action, right? And this action here depends on all the previous observations and actions. Okay. And sometimes the sole reason for carrying out an action is to provide information for future actions. So if you think about diagnostic tests, if you're a medical condition, often diagnostic tests are invasive and often sometimes dangerous and painful, but we do them because we can do future actions are going to be useful. You know, spying is another example of an action that is not useful in itself, but is useful because you find out information. So here's how we're going to formalize it. So what we're going to do is we're going to sequence of decision variables D1 to Dn. And each of these decision variables has an information set of variables we're going to call the parents of them, whose value we're going to know at the time we're making that decision. So we're going to model what information will be available when I get to make a decision. Okay. So what we're going to do is to extend our decision networks. So it's a graphical representation of a finite decision problem. And there are three types of nodes. There are random variables, which we're going to draw as ellipses or circles, and the arcs into them represent probabilistic dependence. So they're exactly the same things we saw with the belief network. Okay. But the other part of it is we have decision variables as drawn as a rectangle. Now the arcs into this node represent what information will be available when the decision is known. So each decision variable has a domain but doesn't have an associated factor. We're not going to start off with a factor in here of which one we're going to do. We're going to try to construct what should the agent do as a function of what it observes. And finally there's utility node, which I'm going to draw as a diamond, and arcs into this represent variables the utility depends on. So the utility has no domain but has a factor on the parents of the node. Just like we did before, we just had single decisions, but now we can have sequential decisions. Okay, here's an example to do this. So the agent, so there are two random variables, the weather and the forecast, and there's a decision variable, the umbrella, and there's utility function, right? So there's one parent of the umbrella, which is the forecast. Okay, so one parent of the umbrella is just the forecast. So what that means is when it has to decide whether to take its umbrella, it gets to observe the forecast, right? So it gets to observe the forecast. However, it doesn't observe the weather directly. So the agent here doesn't get to observe the weather, but instead gets to observe the forecast. Okay, and the forecast, in some sense, is a noisy sensor of the weather. So this is a sensor of the weather. You know, it's information about what's happening outside in the weather system. And we get a forecast that depends on the weather, not independent. We only observe the forecast. We don't decide whether to take an umbrella. But my utility depends on the weather, and whether you take an umbrella. Right? So it depends on those two things. It depends on, the utility depends on that. The utility doesn't depend on the forecast. Whether you're happy at the end of the day doesn't depend on the forecast. Alright, here's another decision node for this. So we have our tampering, alarm, fire, leaving, and report. And now we have a variable called check smoke. So this variable here is called check smoke. So we get to choose whether we check the smoke depending on the report. So that's what this says. So I get to choose whether the agent checks smoke. The agent gets to choose whether it checks smoke, and it's the only information that's available is the report. And there's a variable that says see smoke. Well, you see smoke only depends on whether there is smoke and whether you checked for smoke. And then the agent gets to decide whether should it call the fire department. And it can call the fire department. The information that's available to it when it calls the fire department is whether it saw smoke, whether it checked for smoke, and whether it reported. And the utility here, I'm assuming, only depends on whether there is a fire, whether you check for smoke, and whether you called. So that's all it depends on. So no forgetting decision networks. A decision network where the decision nodes are totally ordered. This is the order that the actions will be taken. All decision nodes that come before DI are parent to the decision node. So the agent remembers its previous actions. Okay, so the agent actually remembered what it did before. It turns out that it's harder to optimize forgetful agents. And any parent of a decision node is a parent of subsequent decision nodes. So it remembers its previous actions, but also remembers its previous observations. So it's a no forgetting decision network. So it's a special type of one. Okay. So now what should the agent do? What the agent should do at any time depends on what it will do in the future. And what the agent does in the future depends on what it did before. Okay. Now we're going to find a decision function for a decision node DI as a function that specifies what the agent should do for each assignment of values to the parents. So when it observes this observation O, it does as function as pi, this decision function is pi of O as a function of what this pi is a function of what you're going to do of the observation. And that's for each decision I. So there's a separate decision function. And a policy is just a sequence of decision functions, one for each decision node. So let's give some examples here. So here's the domain here. There's a forecast weather utility, and suppose the domain for the forecast is they forecast either sunny, cloudy, or rainy. And the umbrella, you can either take it or leave it. Well, here are some of the policies. Now what we're going to do is for each value of the forecast, you get to decide whether you take it or leave it. So that's this function from forecast into umbrella. Okay, so some policies are take the umbrella if it's cloudy, otherwise leave it. Another one is, so we're just going to, if it's sunny, we're going to leave it. If it's cloudy, you're going to take it. If it's rainy, we're going to leave it. Another policy is always take it. Another one is always leave it. So if you think about how many policies there are, well, we can work it out. So when it's sunny, you get to take it or leave it. So there are two choices there. There are two choices for cloudy, and there are two choices for rainy. So it's 2 times 2 times 2. So there are in total 2 to the 3, which is 8 policies. So for each one of these, it gets to choose it or take it or not. Okay. So here's the other example we gave. So all variables are Boolean here, assume. And some of the policies now are, you've got to decide what you're going to do for each of these. You've got to decide whether to check for smoke and what to do, whether to call or not. So one of the policies, never check for smoke, but call if there's a report. Right? Another policy, a different policy, the second policy, is we're going to check if there's a report, we're going to check. If there's no report, we're not going to check. And now we're going to call if there's a report and we see smoke. Okay, so this one here uses the report to check for smoke, and now we're going to see smoke. Another one is always check and always call. So if you think about how many policies there are, well, for checking for smoke, there's 2 for when report's true and 2 for when report is false. So that's 2 times 2 is 4. For call, there are 8 different, there's 3 parents, there's 8 different assignments, so there's 2 to the 8 different values. So it turns out there's 2 squared, which is the number for check for smoke, and 2 to the 8, so there's 1,024 policies. Okay, so now we're going to look at the expected utility of a policy. So what we'd like to do is to find out the best policy, the optimal policy. So a possible world W satisfies a policy if W assigns a value to each decision node that the policy specifies. So if we go back to here, right, in this one here, the only possible worlds are that we're allowing is that check smoke happens to have the same value as report, and call happens to have the same value. It's true if and only if you report and you see smoke. So they're the only possible worlds we're going to do are those that satisfy that. That's all we're saying here. Okay. Now the expected utility is just the utility times the probability, which you did before. An optimal policy is the one with the highest expected utility. So we're going to try to find a policy that has the highest expected utility, and that's the goal of what we're going to try to do. So we're going to try to construct the policy that has the highest expected utility. So if we look at the if you look at this network, then we can try and find out, we can load a decision load a sample problem. If we load one of these decision nodes, let's do the fire alarm decision load, we load this, here's this node, right? So now we can look at this probability table. So we can look at the probability of see smoke. Here it says you see smoke if you check for smoke and there is smoke. So this is not a noisy sensor at all. This is a perfectly deterministic sensor. Okay. There's no conditional probability table for this. This doesn't have a probability or a utility table. And all the rest are exactly the same as we had before. We had the probability of smoke given fire. The other one we have is the probability of utility. And here I'm assuming that you have, if you don't do anything, you get 0 and everything else is negative, right? And it's really bad to have a fire and not to call. If you have a fire and you do call, you get a little bit negative, and it's you don't want to check for smoke. Checking for smoke has a cost associated with it. Okay, so it's not worthwhile to always check for smoke, maybe. All right, so that's what's happening here. And now we can go back to here, we can solve it. We can optimize these decisions, and we'll do this in brief mode. It's just going to do it. It's going to tell me the expected value. And now I can look at what's happening here. So now we're going to check for smoke. As if we look at this and this call, these now have probabilities associated with it. Why? Because they have utility. So here I've got to check for smoke. So here I check for smoke if the report is true, and I don't check for smoke otherwise. That's actually the optimal policy here. The optimal decision function for check smoke. If I look for call, I get to choose whether I call for each report, check smoke, and see smoke. So I call, if all three of them are true, I call. If I've checked it and reported, I don't call. Okay. If I don't check for smoke, then I always call. Right, that's what's happening here. And this one here, and then you say that if there's no report and you do check for smoke and you see smoke, then you should call. And if there's no report and you check for smoke and you see smoke, you should also call, otherwise you shouldn't call. Okay, that's how we're going to do this. That's all you need to do for the next assignment. And next time, the next class next week, is we're going to look at how to solve this with an algorithm to solve it. All right, thank you.